Good afternoon, everyone. I'm going to give it one more minute to let everybody who's logging in finish logging in, and then we'll get started. All right, good afternoon, everyone, and thank you for joining us. This is Sarah Davison with Viavi Solutions Marketing. I want to thank you for joining us on our call today on the Basic Test and Waveform Analysis webinar. I have just a few housekeeping notes to share with you. This webinar is being recorded and will be available for you to review in approximately 24 to 48 hours, and an email will be sent to all attendees with a link to the recorded version. All lines are on mute, but we are monitoring the chat and will answer questions at the end of the webinar or reach out to you individually to ensure you get the answers you seek. And now I'd like to turn it over to our speaker today, Mike Fortna.
Thank you, Sarah. Welcome to the seminar. Again, I'm Mike Fortna. I'll be giving the webinar today, and along with me are Bill Nichols and Dave Hansen. We're all three field applications engineers for Viavi radio test set products. So we're here to help with support on any of our radio test set products. Our emails are visible right there, so you can take a snapshot of that if you need to contact any of us. So for our agenda today, some things that we will hope that you'll learn from the presentation is we're going to cover some of the graphical tools that you can use to evaluate digital transmitter performance. We'll talk about what do those tools tell you, what are the acceptable limits for various digital measurements, and are digital signals just good? Before we get into actually some of those graphical tools, I find that it's always better to make sure everybody has just a fundamental understanding of how this signaling works with some of our digital technologies. So if you look at this graph, the carrier that's meant to be a carrier in the center, and the way our digital radios are working is you can key a transmitter, and I'm going to use Project 25 as an example, but it's true of P25 technology, NXDN, DMR, all of them have these similar characteristics. But we'll use Project 25 as an example. And with that, I can key a transmitter. When I speak into the microphone, it does digitize my voice with a vocoder into ones and zeros. That's data that needs to be transmitted over the airwaves. And the way it's accomplished is we use FSK, frequency shift keying. So the carrier is going to move to one of these four frequency offsets. And I might grab a laser pointer here. So each of these frequency offsets represents a 2-bit pattern. So in the case of Project 25, one offset is minus 1800 hertz, another offset is minus 600 hertz, another offset is plus 600 and plus 1800 hertz. So with these four offsets, the carrier depending on the data that's built up to send out, moves the carrier to one of these 4 frequency offsets. So if it wants to transmit a 1-1, it moves the carrier to 1.8 kilohertz below center frequency. So each of those offsets then represents a 2-bit pattern. The receiver synchronizes with the data, and when it sees the carrier at plus 1.8 kilohertz, it interprets that as a 0-1. So it rebuilds the message based on the carrier offsets. So it'll work a little bit like this illustration here. There's a 1-0, it moved the carrier off to the 1-0, a 0-1, and then 1-1. So even when you're not speaking, when you're transmitting, it's transmitting all these 1s and 0s. So as the data is built up, the carrier just keeps offsetting to the proper 2-bit pattern, and the receiver deciphers that. So there are 4,800 symbols per second, and a symbol is one of those 2-bit places. Since each symbol represents 2 bits, the actual data rate is 9,600 bits per second. But the symbol rate is 4,800 baud. Frequency error is a measurement that we're used to in both analog and digital systems. However, in digital systems, the measurement is done quite differently. The measurement is done, we measure the frequency error of each symbol. So in analog mode, we would just measure the carrier frequency, but it can't be done that way with digital signals. So we measure the frequency error of each symbol, we sum those together and divide by 4 to come up with what the actual frequency error is. So, and with a digital Project 25 signal and an analog service monitor, it's not going to give you the 0 hertz frequency error. It's going to kind of gravitate to where the data is more prevalent. So simultaneously, when we're making a frequency error measurement, we're also measuring symbol deviation. So we measure the deviation of each symbol, and this is done over 144 symbols. And the meters will show a single value of 1800 hertz in that example, but it's actually measuring the deviation of each symbol and then summing those together, dividing by 4 again, and equating that to a single symbol deviation based on 1800 hertz, or actually not 1800, but whatever the maximum symbol deviation value is. In Project 25, the outer limits are 1800 hertz. DMR is 1944 hertz, so it's going to be based on the type of modulation or technology being used. So now we'll look at some of the digital measurement tools. There's a constellation plot. This is another example of a constellation plot, but with 64 QAM type modulation. This is a distribution plot. And this is the distribution plot again, but this is looking at HCPM modulation. So one thing you can see is that even with the same type of plot, if the signal is different, it's going to appear differently. A DMR eye diagram. And again, this is an eye diagram, but this is of a P25 LSM signal. So just by looking at it, I can see that what type of signal it is. That's an eye diagram of a phase 2 HCPM type signal. A trajectory plot, this gives us different information. It's a power magnitude plot. Another trajectory plot, but if I'm receiving this off the air, I could tell immediately that that was an LSM base station I was receiving. And another trajectory plot, this is a CQPSK type modulation. With TDMA type signals, it's useful to see power profile plots. So this is a power profile ramp. And then a full power ramp that shows the entire power cycle of a ramp. And then there's a power over time plot that can show us if power is varying over time. So each of those different graphical tools can reveal a unique or different types of signal impairments. So you can see different impairments with different tools. So one type of signal impairment is modulation fidelity or FSK error. And I'm going to zoom in on this real quickly. And this is an example of a good signal, what a good signal would look like. I can see on the distribution plot that the signals are fairly clean or narrow lines. On a constellation plot, it's kind of a small dot that's landing within the target areas. And on the eye diagram, I see there's a tight intersection point on the center dotted line. If I look at this signal, a signal that has modulation fidelity or FSK error of 6.3%, I can see that on this distribution plot that it looks noisy. On the constellation plot, I can see that it's not a fine dot, it's more of a spread across. The constellation plot is actually like looking at the distribution plot from the top down. It's another way to look at that. And the eye diagram, I can see it doesn't have as tight of an intersect point as we had with the good signal. So how does the signal get that way? Unfortunately, almost all radios allow us to make adjustments that can make this happen. So usually there's a deviation balance or modulation balance, some type of deviation adjustment that if it's not done precisely, you'll end up with a signal that has high modulation fidelity. That's why specifications on test equipment are pretty tight for modulation accuracy measurements. Most manufacturers like 2 to 3% accuracy on a deviation meter to be able to make these alignments. The maximum allowed FSK error or modulation fidelity is 5%. So the impact that high mod fidelity causes is it can impact your coverage area. So actually all of these different signal impairments we're going to look at today can impact coverage area. And not only can you have just one, but you can actually have all of them at the same time. And when combined, it's especially hard for the receiver to decode these signals. So mod fidelity, or FSK errors, is basically a quality measurement of the digital transmitted signals, the RMS deviation error expressed in a percentage. And most commonly, what causes it is a deviation alignment. Symbol deviation is another thing that can be impacted by a different deviation adjustment in a radio. Usually it's the deviation limiting or max deviation adjustment. The maximum allowed symbol deviation error is 10% of the outer symbol. So in the case of Project 25, the outer symbol is 1800 hertz. So 10% of that would be 180 hertz. In DMR is 1944 hertz is the outer symbol, so it would be 194 hertz in that case. So the deviation of each symbol is ratioed, and I'm going to zoom in on this. That froze it. So again, this is the good signal, and this is a case where the symbol deviation the symmetry is not right, so the symbols don't line up on the dotted lines. So many people may have not seen what bad signals look like, but this is what it looks like. So I can see on a distribution plot that they don't line up on the dotted lines. The constellation plot shows that the signals are landing outside of the target areas. And the symbol deviation that should be 1800 hertz in this case is showing 2047 hertz, which is beyond the 1980 hertz that would be allowed. So that signal is failing and would cause an issue for the receiver to decode it, which impacts, again, coverage area. One other thing I'll point out on the distribution plot, as you'll see, these symbols are showing different amplitudes. This is not a signal power measurement. It's an activity measurement. So what this plot is telling me is that this symbol here is active more often than this symbol. So it is symbol activity. Okay, so we talked about this a little bit already. This is a chart that shows some of the different symbol deviations or symbol offsets based on technology. Project 25, phase 1 is plus and minus 1800 hertz on the outer symbols and plus and minus 600 hertz on the inner symbols. And that's, let me grab that laser pointer again. So that's this chart here, the phase 1. Phase 2 HCPM, you can see there's more symbols. The outer symbols are 3 kilohertz. Phase 2 HD QPSK type modulation, the outer symbols are 2250 hertz. DMR, which is a TDMA type modulation, so it's transmitting in 30 millisecond bursts, but during that 30 milliseconds, it is doing the FSK shifting to transmit the data. So this plot also applies in DMR. And the outer symbols there are 1944 hertz. NXDN has 2 different baud rates associated with it, 4800 for very narrow and 9600 baud. And I can see that the 4800 baud NXDN only occupies 6.25 kilohertz bandwidth, and the 9600 baud of NXDN occupies 12.5 kilohertz of bandwidth. So symbol clock error. This is a somewhat uncommon issue, but I've seen it at least 3 times. And is most easily detected with the eye diagram. And on the eye diagram, what you look for is it should intersect on the dotted line in the middle. But when you have an issue with symbol clock error, it will actually shift above and below that center line, and it will make the distribution plot look as though there's FSK error, or make that value look higher. But if you look on the eye diagram and you see it shifting around, it's really because of a symbol deviation error, or symbol clock error rather. So symbol clock error most commonly is expressed in parts per million. For project 25 in NXDN, the maximum allowed error is 10 parts per million. DMR, 1 part per million is the maximum. It can also be expressed in millihertz because it is a 4800 baud rate. This is a measurement actually of that 4800 baud symbol clock. Now, one thing is for sure is you'll never see this kind of issue or many other digital issues with an analog service monitor. A little bit about trajectory plots. Again, a trajectory plot will show from the center going outward is a power magnitude measurement. So with C4FM, which is used with Project 25 Phase 1, that's a constant power type modulation source. So on the trajectory plot, it appears as a circle because the power is constant. And that's what I would expect to see. If the power were fluctuating, I would actually see that. It wouldn't be quite like a circle like that, but I would be able to see power fluctuations. And this is the associated bandwidth that signal occupies on the spectrum analyzer. So this is an example of linear simulcast modulation. This type of signal is only transmitted by a base station. It's a complex waveform where the power varies between symbols. So on that distribution plot, when it's going from one symbol location to another, the power actually droops from one symbol location to another. But at symbol time, it's always at the proper power level or the same power level. So you can't use a standard broadband power meter to measure a signal like that. You would have at least a 3 dB error because it's going to try to pick up on the average of the power. Since it's always fluctuating in power from one state to another, a digital service monitor will measure the power at symbol time. So it's always going to measure power at these peaks at symbol time. And down below, that signal also occupies 12.5 kilohertz, and we can see that on the spectrum analyzer. This is another form from another manufacturer. It's called WCQPSK. Again, that's also a 12.5 kilohertz bandwidth. I might mention also another thing I can see on an LSM plot or a trajectory plot, and I'll use the LSM as an example, is that type of signal requires a linear power amplifier. If that amplifier were to go into compression, I would see the center of that diagram kind of try to spread out and look more like a circle. It'd be showing me that the power amplifier was in compression. And finally, this modulation format called CQPSK. This is actually a 6.25 kilohertz modulation scheme. This is what in the beginning people thought what might end up being phase 2. That never did happen. We went on and they developed HCPM and HDQPSK modulation types to be our phase 2 standard. I mention this modulation only because some radios will show that there's some programming for CQPSK. Simply means that the radio is programmed to receive a modulation type that's not constant power. It can be or it cannot be. It'll accept both. But if that's not programmed that way, it wouldn't work with a signal like LSM or WCQPSK. So for DMR and other technologies that might use TDMA, there's measurements for called magnitude error. DMR allows a maximum magnitude error of 1%. And what we're looking at here are examples of a good signal. First of all, there's a, let me get the laser pointer again. There's a power profile full. This shows an entire 30 millisecond power burst. And what you look for on something like this is I should see the signal come up within the window, and then it should drop down within the window. And the power should remain a constant power throughout the 30 millisecond time burst. This particular graph has markers to measure the power at various points along that in that time to see that the power is indeed the same power level. There's a power profile ramp graphic that shows the first 3 milliseconds of the power ramp up, which is over here. It's like a magnified version of the first 3 milliseconds of the full power profile. And it shows the last 3 milliseconds of the ramp down. So the ramp up and the ramp down should appear within the window. If it were to appear drop down outside of the window or come up outside of the window, then it's in the power is actually in a different time slot, and that can be an issue. So we saw the good signal. Here's some examples of a bad signal. The full power profile is showing us 2% magnitude error. Actually, the value you get from the meter, there's a meter that's going to reflect this. The graphics just show us the issue so we can see it graphically. But there's always a numeric meter that gives us what the actual value is. And we'll maybe possibly zoom in on this a little further. You can see a slight droop on this signal from beginning to end. And on the ramps or the beginning 3 milliseconds is higher than it is at the last 3 milliseconds. So that's actually an issue for magnitude error. And this smaller picture here is actually a picture of a real radio issue that we took a snapshot of. It's got different issues. It's kind of a little ramp up problem there, and it ramps down outside of the 3 millisecond close window, where it should come down within the window, and it does not. So it's actually transmitting power into an adjacent time slot. So that will cause interference with that time slot. This image here, again, this is a measurement from a real radio. And you can see at the beginning, it kind of comes over and then it's got a shelf, then it comes up and it comes out. This was actually caused because of the battery voltage. So when the battery was fully charged, this radio would show this 2.2% magnitude error. As the battery drained down a little bit, the radio worked properly and showed a very small amount of magnitude error, and the shelf went away. So let me remove that. We double checked this using a power supply. And when we connected the 7.5 volt power supply, the radio performed perfectly. As we bumped it up to 7.7, 7.8 volts, that's the shelf just popped up and it had bad magnitude error. So there's just different things that can cause these issues, but still it's going to can cause an interference. If you had overshoot on the ramp up, that could cause some spectral regrowth and spurious signals in the spectrum, or that interferes with a lot of things. Another kind of common test is testing a transmitter bit error rate. This will almost always result in a 0 reading when you're testing a transmitter directly. The measurement on transmitter bit error rate is actually more useful in drive testing, where I'm receiving a signal off the air. But some of the common patterns that we would use is for project 25, we use a 1011 pattern. NXDN, DMR use a 1031 pattern. Some base stations will use a V.52 or O.153 or a standard 511 pattern. All three of those patterns are identical with different names. So test equipment may only show one of those, but it's important to know that if the test equipment only offers a standard 511, to know that that's equivalent to an O.153 or a V.52 pattern. Viavi products have a pattern called frame sync. This is very handy to use because you can only, normally the bit error meter is expecting that the transmitter is transmitting one of these patterns, like a 1011 or a 1031 pattern, and you have to tell the bit error meter what pattern that it's receiving, and then it'll show you what the error is from that pattern. To get the radio to transmit that pattern to begin with, it's generally connected to a computer, and which is controlling the radio to make it transmit one of those test patterns. With a frame sync pattern, we can measure a transmitter that's just transmitting a voice. We can measure the bit error of a control channel. So that makes it very useful for testing, drive testing a control channel, because you don't have to take the station out of service. You can leave the station in service. The other method would be to take the base station out of service and make it transmit a 1011 pattern, so that you could then do your drive test measuring the 1011 pattern. But with frame sync, you don't have to do that. You can leave the base station in service and do a drive test to see where you might have a bit error rate. So with digital signals, it's in coverage area, this signal strength isn't the only thing that's important. You can have a high signal strength and also have a high bit error rate because of multipath or other issues. So there's a variety of measurements that need to be made on a digital signal other than just signal strength. So on the receiver side of that, we test the sensitivity of a receiver using those same types of patterns, a 1011, a 1031, and a service monitor will inject a signal that has one of those patterns. I'll say a 1011 as an example. And generally this is done at a low level, like minus 116 dBm or lower. And a computer would be connected to the receiver, and it would interrogate the receiver for what its received bit error rate was. So you can actually adjust the level down until the receiver indicates a 5% bit error rate. Most people just inject the required amount and see that it's at least better than 5% at that level. So if you don't have the PC connectivity to the receiver to see exactly what it is, some service monitors have like a speech pattern built in. You can inject that into the receiver and drop the level until you can't understand the speech any longer. And that then becomes the usable sensitivity of the receiver in an informal manner. If you can't understand what's being said, then it's not usable. One thing you should be aware of is there are other signals that can interfere with the receiver testing. This spectrum analyzer image you see on the left is actually a signal that was off the air here, and it interfered with the receiver testing. So if I put on a laser pointer here, there are different things like you should always kind of be conscious of the cable type you're using. You should use a double shielded cable. I've seen cases where like an adapter on the radio wasn't tight and it was loose. Signal can get into that. And what I'm seeing on this analyzer, these are actually pretty strong signals, like minus 40. And it would cause the radio to fail the receiver sensitivity test. I can take our equipment to a trade show. A receiver will never pass a receiver sensitivity test in that environment because of all those strong signals in the area. So some solutions would be to have some type of case that you can put the radio into, or a screen room or something like that to shield yourself from the outside world. So do signal impairments impact coverage area? Yes, they do. Most of the time, the signal impairments that we've looked at so far are indeed caused by deviation alignments, or that's the worst. Those cause the worst signal impairments. They cause issues with modulation fidelity. They cause issues with symbol deviation, and you could have both or multiple signal impairments. So, and that can occur on a base or subscriber radios. I've actually seen cases where people misaligned almost all of their subscribers over time, and their system had some pretty bad issues. But most of these problems can be resolved with simple alignments. So if you look at these graphs, it's showing a kind of a coverage area with a 100-watt transmitter, and the coverage area with a 50-watt transmitter, and then the coverage area with a 25-watt transmitter. So 50 watts is 3 dB down from 100 watts, and 25 watts is 6 dB down from 100 watts. So what I'm trying to illustrate here is that if you have a signal impairment that impacts the receiver sensitivity by either of those amounts, like 3 dB or 6 dB, in other words, it takes 3 dB more signal for the receiver to pick up the signal, then that signal is the equivalent of putting out half the power, or 25 watts instead of 100 watts. And that's all because of deviation alignments. So you don't want to, just because you have coverage areas or coverage issues, it doesn't mean you go to the base stations and crank them up for more power. You know, we need to look into it more deeply and see what the actual root problem is. So again, this can be a problem at the base or subscriber side. Most problems can be resolved with simple alignments. So in summary, graphical tools can aid in a diagnosis of digital issues. I can see exactly what's going on graphically, and then there's numeric values to back those things up. So digital signal impairments impact coverage area. The distribution and constellation plots can easily show symbol deviation error or high FSK modulation fidelity error. The eye diagram can show what signal type is being received. Can also show symbol clock error issues. And the power profile ramps can show any magnitude error issues which could be power amplifier related or power supply related. So those are all issues that can be detected just from looking at some of the graphical tools and the digital analysis measurements that are available on the digital service monitor. Speaking of digital service monitors, here's 3 of the Viavi products. The flagship 3920B, the Viavi 8800SX, and the small and portable 3550R. These are all products that are available here. And with that, thank you for your attendance, and hope you found the webinar with some useful information, and I'll hand it back to Sarah.
Thank you, Mike. And now that concludes today's webinar, and I want to thank you all for attending. When you exit today's webinar, you will see a short survey asking you for feedback. I would be grateful if you could spend a few minutes completing this to ensure we maximize the value of our webinars to you. Again, you'll receive a recording of this webinar, and I'd like to thank you. Have a great day.